The first heterocycle we are going to learn is Pyrrole with the formula C4H4NH. It's a colorless volatile liquid that darkens readily on exposure to air. Boiling point is around 131. So it's present in most of naturally it's present in vitamin B12, bile pigments like bilirubin, bilirubinin, porphyrins of heme, chlorophyll, etc. So this is basically present in most of your natural products. Okay, these are some of the structures like chlorophyll, porphyrin ring, and hemoglobin. So all this contains your pyrrole ring. Now some of the structures, as we said, it has got 3 pairs of delocalized pi electrons. It has got 3 pairs of delocalized pi. 2 pairs are shown as bonded. Okay, you got a double bond between the second and the third carbon, and fourth and the fifth, and the third lone pair of electrons comes from your non-bonding electrons of your heteroatom, that is oxygen. So all these non-bonding electrons are in the sp2 hybridized orbitals perpendicular to the p orbitals. Okay, so this non-bonding orbital is always perpendicular in the p orbitals, and they delocalize and they are perpendicular to the plane of your sp2 hybridized. All this, if you see, in case of Pyrrole, it is cyclic, planar with all the 3 delocalized pair of electrons, and 4n plus 2, that is your Huckel's rule, is satisfied. That's the reason why they fulfill the criteria for your aromaticity. They fulfill the criteria for your aromaticity. And we know it can undergo titration because tautomerism because of the migration of electrons from your nitrogen to your carbon, and that's why you get 1H, 3H, and 2H pyrrole depending upon the migration. In the case of first migration, the hydrogen gets migrated to the third carbon. In the third structure, you can see the hydrogen is at the second carbon. So these are the various tautomeric forms of your pyrrole. Moreover, your pyrrole, it can form intramolecular hydrogen bond between the adjacent. Within the structure, it will form intramolecular hydrogen between your nitrogen and your hydrogen of your adjacent within your adjacent ring. The second type is intramolecular, that is between hydrogen bonding between the NH and the pi electrons of your adjacent. So this is known as intermolecular, and other one is your and because of this reason, pyrrole has got high boiling point because extra energy is used to break this hydrogen bond. That's why pyrrole has high boiling point. So this is the basic structure. So there is a CC pi bond, CC sigma bond between your third and the fourth, and rest between C2 and C3 and C4 and C5. There is an sp2 hybridized unsaturation is present, and all the pi orbitals are perpendicular to the sp2 hybridized orbitals of your pyrrole. Okay, and the lone pair of electron, unpaired pair of electrons in your nitrogen is perpendicular to the plane of sp2 hybridized nitrogen. Okay, so this is the structure of your, and the electrons in the pi orbitals are delocalizing across the system. This is the reason why your pyrrole is aromatic in nature. These are the resonating structure. First thing, what you have to see the movement of electrons. Most important thing that has to be monitored is movement of electrons. Okay, so first is movement from lone pair of nitrogen from nitrogen to the between nitrogen and the C1. So in doing so, the electron density gets increased in your third carbon. Nitrogen gets positive charge. The charge in your group, in your molecule, is very much important. In the heterocycle is very much important. The positive charge will always be on your heteroatom. The positive charge will be always on your heteroatom, and just you keep on moving the bonds till you get the original structure of your pyrrole. Okay, So this is how you write the resonating structure of your pyrrole. Then from the third position it goes to the fourth position. Again it comes to the second position, and if you see at all these positions there is an electron density at 2, 3, 4, 5, all the positions. So this is why pyrrole favors your electrophilic aromatic substitution reaction. Okay. Now let's go for the first synthesis of your pyrrole. It is known as nor-pyrrole synthesis. What is that reactants in this? You get an alpha amino ketone. What is alpha amino ketone? That is an amino group which is at the alpha neck adjacent to your carbonyl carbon. Okay, adjacent to your carbonyl carbon. Okay, that's a and you treat it with beta dicarbonyl derivative. Any beta dicarbonyl derivative. Okay, in presence of a base. Okay, in presence of a base, you get your substituted pyrrole. Now let's go for the mechanism of action. Since the reaction takes place in presence of the base abstracts the proton, methylenic proton, between the two dicarbonyl compounds. Okay, that forms a carbanion. This carbanion attacks on the carbonyl group of your alpha amino ketone to form your OH. Okay, to form your OH, and your nitrogen attacks on the carbonyl group. So this leads to the formation of a diols type of system. Okay, and there is a loss of water molecule. There is a loss of water molecule to give you your unsaturated, that is your pyrrole. And since these groups are esters, okay, the group is an ester, so it can be hydrolyzed to get your carboxylic acid, which can undergo decarboxylation by heating to get your substituted pyrrole. So this is how you can prepare yours. So what is the first step? Generation of a carbanion attack on the carbonyl carbon of your alpha amino ketone. Simultaneously the nitrogen attacks on the beta carbonyl of your beta dicarbonyl compound. So it undergoes cyclization, OH gets removed by dehydration, and you get your substituted pyrrole. You get your substituted pyrrole. This is the first mechanism for synthesis of your, that is NOR synthesis. What do you take? You take an beta dicarbonyl compound and react it with alpha amino ketone in presence of a base. Generation of your nucleophile which attacks on the carbonyl carbon of your amino ketone. The amino group of your amino ketone attacks on the carbonyl carbon, and thus it undergoes cyclization, which is followed by dehydration to give your substituted pyrrole. Okay. Now the next Hans-Fitz synthesis. Hans-Fitz synthesis. In this you take an alpha haloketone, okay, and you take a beta ketone or beta dicarbonyl compound, same as that of it. So instead of your amino group, you take a chloro group, and you take an extra amino group. Instead of your, you treat it with an amine, you take an alpha haloketone and a beta ketone. You treat it together, okay? You treat it together, or basically you take ammonia or any substitute. If you want a substituted amine pyrrole at the nitrogen, you take an substituted amine, you will get a N substituted pyrrole. Okay, so depending upon that, either you can take an ammonia or a substituted ammonia amine. Okay, so you get your cyclized product, that is your pyrrole. The reaction mechanism is same as that of your this thing. Amine gets added over here, you get an alpha amino ketone. Similarly, in presence of base, it undergoes cyclization. So it's the same. Amine attacks on the carbonyl, you get your NH2. That will, so double bond imine is formed. That imine, okay, and gets converted to the tautomer enamine. That is shifting of the bond, and this will attack on your carbonyl compound. Okay, this will attack on your carbonyl derivative, and you get a cyclized product which is similar to that of your previous reaction, that is your NOR synthesis. And this is the mechanism of action of your Hans-Fitz reaction where you take ammonia, beta dicarb, that beta keto ester, and alpha halo keto. In presence of ammonia, you get your pyrrole. You get your pyrrole. You get your pyrrole. Okay. Get your pyrrole. Okay. You get your pyrrole. So, what is the next reaction now? This was your second method of synthesis. Palnar synthesis, we said. Palnar now synthesis what? 1,4-dicarbonyl compound react with ammonia or a primary amine. You get a substituted. So you directly take a dicarbonyl compound, you treat it with ammonia, you get your substituted pyrrole. That is your Palnar synthesis. That is a mixture of two. Palnar synthesis is nothing but your treatment of dicarbonyl compound with your ammonia or a substituted amine to get your corresponding substituted pyrrole. Okay. So what is the mechanism of action? Let's go for the mechanism of action. Okay. So you got a 1,4-dicarbonyl compound. It undergoes ketoenol tautomerism. Then amine, when you heat it with amine, you get. So what happens? The amine attacks on. You get, when you heat it, you get your pyrrole. So mechanism. What does it make? What is seen? Your amine attacks on your carbonyl carbon. Okay. There is OH, and again the amine attacks on your carbonyl too. So it forms a cyclic core. And this in acidic medium, it undergoes dehydration to give your pyrrole. So this is your third method. Now the fourth method is obtained by succinamide. When you succinamide is treated with zinc dust. When the succinamide is treated with zinc dust, it undergoes reduction to form your pyrrole. So when you treat succinamide with your zinc dust, okay, heat it, you get your pyrrole. You get your pyrrole. This is the fourth method for the synthesis of your pyrrole. This is the fourth method for the synthesis of your pyrrole. So these are the methods. Now let us go for the properties, physical and chemical properties of your pyrrole. So what is it? Now it is said that pyrrole is amphoteric in nature. What do you mean by amphoteric? It can react with both acid as well as base. Pyrrole is a weak base because of the lone pair of electrons on the nitrogen, which contributes to the 4n plus 2 pi electron club. So it is weakly basic because of the lone pair of electrons. Okay, hence the availability of electrons is decreased, and consequently it is a weak base. If it was free, then it would have been a stronger base. If the lone pair of electrons, because basicity depends upon the availability of your lone pair of electrons on your nitrogen. Since the lone pair is involved in your formation of your aromaticity, that is your sextate, so that's why your pyrrole is weakly based. Pyrrole exhibits its acidic property. So what happens? It can react with potassium hydroxide to form your potassium pyrrole derivative, because your potassium hydroxide can abstract the proton from your nitrogen to form your potassium pyrrole. That's why pyrrole is said to be amphoteric in nature, weakly basic because of the presence of the lone pair, and acidic because it can react with KOH to form your potassium salt of your pyrrole. That's why it is amphoteric in nature. Okay, now let's go for the electrophilic substitution. And if you see, when an electrophile attacks, C2 and C3, let us see what happens when it attacks on the C2. Your positive charge is there. So there are three possible resonance structure when there is an attack on the C2 carbon. And when there is C3 carbon, there are only two resonating structures. Thus, when the electrophile attacks at the second position, C2 position, there are extra resonating structures. Okay, there are, as compared to that of your C3. So whenever there is more resonating structure, that means the compound is more stable. That's why your pyrrole undergoes electrophilic substitution reaction at the second position. It prefers the second position. The preferred position is your second carbon. So your electrophilic substitution basically takes place at the second position. Why? Because there are more resonating structure as compared to that of your C3. Why? Moment the positive charge comes on the nitrogen, it destabilizes the structure. Okay, it destabilizes the structure. Okay, so in case of C2, the resonating structures are 3, whereas in case of C2, there are 3. In 2, when the attack takes place on C2, there are 3 resonating structures. When it takes place on the C3, there are only 2 resonating structures that contributing to stability. So this is why the electrolytic substitution reaction takes place at the second position. So let us take some examples of your electrophilic substitution. So what is the first thing in acidic medium? So what happens? This acid attacks on your second position. So what this leads to a formation of your 3H pyrrolium ion. Similarly, it can also form 2H pyrrolium ion. Okay. So these are the two products that are formed on when you treat it with acid. So there will be an increased in hydrogen at the second or the third position. That is your 3H pyrrolium ion or 2H pyrrolium. What are the other reactions of this thing, electrophilic substitution? So it requires milder conditions. So what it takes with your nitroacetate in presence of your nitric acid. That is, when you treat nitric acid in presence of your acetic acid, you get your 2-nitro 1H pyrrole. So it requires milder condition. It does not require harsh conditions. It reacts with pyridinium sulfate to form your sulfonate, 2-sulfonyl acid, pyridine to sulfonic acid. It reacts with chlorine to form 2-chloro 2-chloro 1H pyrrole, and it reacts with acetic anhydride in presence of BF3. That is your Friedel-Crafts reaction to form 2-acetyl 1H pyrrole. So these are the examples of electrophilic substitution reaction: nitration, sulfonation, chlorination, and acetylation. That is your Friedel-Crafts acylation. Now what is the next reaction? It reacts with your potassium carbonate. It reacts with your aqueous potassium carbonate. When you heat it with aqueous potassium carbonate, it undergoes Kolbe-Smith carboxylation. That is introduction of your carboxylic group. Introduction of your carboxylic group at the second position. So that is known as Kolbe-Smith carboxylation. Kolbe's reaction you might have studied even in phenol. Similar to that, it also undergoes Kolbe-Smith carboxylation at the same to give 2-pyrrole to carboxylic acid. Next is Remer-Tiemann formylation. Similarly, the reactions are similar to phenol. So pyrrole reacts with chloroform in presence of KOH to form pyrrole 2 aldehyde and also another product, that is 3-chloropyridine. So ring enlargement also can take place when it undergoes Remer-Tiemann reaction, and you get a pyrrole 2 aldehyde or 2-formyl pyrrole. So this is Remer-Tiemann Kolbe reaction similar to that of your phenols. It also undergoes diazonium coupling. Why? Because it has got electron rich position at your second end. Basically, it undergoes diazo coupling at the second position to form 2-phenyl aza 2 pyrrole. So it also undergoes diazonium coupling because of your increased electron density at the second position. Because when you see the resonance structure, there is an increased electron density at the second position. That's why it also undergoes an azo coupling. It also undergoes a azo coupling to give 1-phenyl aza 2 pyrrole. To give 1-phenyl aza 2 pyrrole. Reduction. So what is the product of reduction? If you treat with zinc acetic acid, okay, at room temperature, you get 2,3 dihydropyrrole. You get 2,5 dihydropyrrole. Means there is a shifting of the double bond. There is a saturation at the 2 and the 5th position. Okay, you get it. And when you treat it with palladium fully at high temperature, you get pyrrole. Fully saturation takes place when you treat it with zinc, platinum and hydrogen. Full saturation takes place when you treat it with zinc and acetic acid. You get your 2,5-dihydropyrrole. So these are the reduced product. It undergoes oxidation in presence of potassium dichromate and acetic acid to give you malic amide. You give malic amide. To give you the malic amide. Okay. So this is your oxidation product of your pyrrole. Oxidation product of your. So it also undergoes ring expansion. What do you mean by ring expansion? There is a ring expansion. So it will undergo ring opening. Sorry, it's a ring opening reaction. This thing has come down and up. So when pyrrole reacts with hydroxylamine in presence of ethanol, you heat it, it undergoes ring opening reaction to form succinyl aldoxane. Okay, succinyl dialdoxane. So it forms an ring opening takes place and you get your oxime. Ring expansion, you treat pyrrole with sodium methoxide in presence of methylene, diadomethylene, you get your pyridine. Okay, you get your pyridine. So this is an example of your ring expansion. So that's just there was a mistake. Your headings have been flipped out. So just remember. So it undergoes ring expansion. Ring expansion by what? That is enlargement of the ring by treatment with sodium methoxide and diiodomethylene. You get your pyridine. And it undergoes ring opening when you treat it with hydroxylamine to give in presence of ethanol. You heat it, you got succinyl dialdoxane. That is 2-aldehyde oxime is formed. Oxime NCH double bond NOH group will be added. So that is known as succinyl aldoxane. So this is your ring opening reaction. Some of the analogs and its derivatives are 1 pyrroline, 2 pyrroline, 3 pyrroline, depending upon the position of your double bond. And the fully saturated structure is your pyrrolidine. Fully saturated derivative of your pyrrole is pyrrolidine. Okay, and these are partially unsaturated pyrrolidine. Okay, so commercial use. Pyrrole is essential for production of many chemical compounds, chemicals. N-methylpyrrole used as a precursor for N-methyl pyrrole carboxylic acid is a building block for various carboxylic acid. Your many reagents are prepared using chemicals are prepared using this pyrrole. It is used as an additive to. It is used as an additive to cigarettes. It is typically listed as a constituent of tobacco smoke, not as an ingredient. It's a part of your tobacco smoke also. Some of the example containing your pyrrole ring. Okay, pyrrole ring. So example is glycopyrrolate. It is an anticholinergic drug used in peptic ulcer. It is an anticholinergic drug which is used in your peptic ulcer. Other example is atorvastatin. So atorvastatin is used for your atorvastatin is used for your high BP. It's used for your high BP. It is an HMG-CoA inhibitor, which inhibits your cholesterol biosynthesis. Atorvastatin, that is management of your cholesterol. So these are the examples of a drug. Another example is your anti-muscarinic drug. Okay, this blocks the activity of muscarinic acetylcholine receptors. Example is procyclidine. Example is procyclidine. Okay, example is your procyclidine. So it is muscarinic receptor which responds to muscarine neurotransmitter and nicotinic receptors which respond to nicotine. So they block both the acetylcholine receptor. That is procyclidine is the example of your drug. Is the example of the drugs containing your pyrrole or its derivative. Okay. This is similarly why the reaction takes place for all the 5-membered ring containing heterocycle. The reaction is taking place at the third. This is the reason why there is more 2 and 5, because there is more resonating structure compared to that of 3. Only when the second and the fifth position is blocked, then only the reaction takes place at the at the third position. Okay, whenever the second and the fifth position is blocked in Pyrrole, then only your electrophilic substitution reaction takes place at the third position. Okay, so this is about Pyrrole.